Welcome to Chapter 6 on halogen compounds. In this section, we'll explore what halogen compounds are, how they're classified, and the key patterns that govern their structure and behavior. Halogen compounds are everywhere in chemistry, from simple alkyl halides to complex aromatic systems, and understanding them is essential for predicting reactivity and synthesis. Halogen compounds are organic molecules where a halogen atom, such as chlorine, bromine, fluorine, or iodine, is bonded directly to a carbon atom. These compounds fall into two main categories based on where the halogen sits. If the halogen is attached to a saturated hydrocarbon chain, we call it an alkyl halide or haloalkane. If it's attached to an aromatic ring, it's called an aromatic halide. This distinction matters because the chemical properties and reactivity differ significantly between the two types. Position isomerism occurs when two compounds share the same molecular formula but have their substituent groups attached at different positions on an aromatic ring, typically a benzene ring. The key insight is that even though the atoms are identical and bonded in the same overall pattern, their spatial arrangement creates distinct molecules with different chemical and physical properties. This is particularly common in aromatic chemistry, where we describe positions relative to an initial substituent using terms like ortho, meta, and para. The formation of position isomers in aromatic systems involves electrophilic aromatic substitution mechanisms. When a benzene ring undergoes halogenation, say with HBr, the incoming halogen can attach at different positions relative to existing substituents. The mechanism proceeds through a carbocation intermediate, and the position where substitution occurs depends on the directing effects of groups already on the ring. Electron-donating groups like methyl direct incoming electrophiles to ortho and para positions, while electron-withdrawing groups direct to meta positions. This is why we observe multiple position isomers as products. Now we're moving into the practical synthesis of alkyl halides. There are three major routes chemists use to prepare these compounds. First, converting alcohols to alkyl halides using hydrogen halides or reagents like phosphorus tribromide and thionyl chloride. Second, adding hydrogen halides across alkene double bonds. This follows Markovnikov's rule, meaning the hydrogen adds to the carbon with more existing hydrogens. Third, free radical halogenation of alkanes, which requires UV light or heat to break the halogen bond. Notice that fluorine is most reactive toward alkanes, while iodine is least reactive. This trend is crucial for predicting reaction outcomes. The conversion of alcohols to alkyl halides depends heavily on the alcohol structure. For primary alcohols, HX works well through an SN2 mechanism. The halide directly displaces water. For secondary and especially tertiary alcohols, PBr3 and SOCl2 are preferred because they avoid carbocation formation and the rearrangements that come with it. When HX reacts with tertiary alcohols, an SN1 mechanism dominates, creating a carbocation intermediate that can rearrange to a more stable structure, sometimes giving unexpected products. The key takeaway: choose your reagent based on whether you want to avoid rearrangement or whether the alcohol's structure makes rearrangement unlikely. We're now diving into nucleophilic substitution reactions, one of the most important reaction types in organic chemistry. When an alkyl halide, that's a carbon chain with a halogen attached, encounters a nucleophile, a negatively charged or electron-rich species, the nucleophile attacks the carbon and the halogen leaves as a leaving group. This fundamental process is the foundation for understanding how many organic transformations occur. The SN2 mechanism is a single-step process where the nucleophile and alkyl halide collide and react in one concerted motion. The nucleophile approaches from the backside, the side opposite the leaving group, and as it forms a bond with the carbon, the CX bond breaks simultaneously. This backside attack causes the stereochemistry at the carbon to invert, a phenomenon called Walden inversion. Because both the nucleophile and substrate are involved in the rate-determining step, we call this bimolecular nucleophilic substitution. The SN1 mechanism is fundamentally different. It occurs in two steps. First, the CX bond breaks slowly to form a carbocation intermediate, a positively charged carbon with only 3 bonds. This is the rate-determining step. Then, in the second fast step, the nucleophile attacks this carbocation from either face, front or back, leading to a mixture of stereoisomers. Since only the alkyl halide participates in the slow step, we call this unimolecular nucleophilic substitution. The structure of the alkyl halide is the most critical factor. Primary alkyl halides undergo SN2 because the nucleophile can easily access the backside of the carbon. Tertiary alkyl halides favor SN1 because the bulky groups shield the backside, making backside attack impossible. Instead, the CX bond breaks first to form a stable tertiary carbocation. secondary substrates can go either way, depending on conditions. Strong nucleophiles and polar aprotic solvents like DMSO push the reaction toward SN2, while weak nucleophiles and polar protic solvents like water favor SN1. A good leaving group is one that can stabilize negative charge well. In other words, it's the conjugate base of a strong acid. Iodide is the best leaving group because HI is a very strong acid. Bromide and chloride are also good. Fluoride is a terrible leaving group because HF is a weak acid, making fluoride a strong base that doesn't want to leave. Water and alcohols are moderate leaving groups. This is why we often need to activate alcohols by converting them to tosylates or mesylates to make them better leaving groups for substitution reactions. Nucleophile strength depends on the solvent. In polar aprotic solvents like DMSO, which don't form hydrogen bonds, nucleophilicity follows basicity, so the order is iodide, bromide, chloride, fluoride. But in polar protic solvents like water, hydrogen bonding weakens larger anions, reversing the order to fluoride, chloride, bromide, iodide. Charged nucleophiles like alkoxides, thiolates, and cyanide are generally strong. Neutral nucleophiles like ammonia and water are weak. This is why we choose our solvent carefully depending on whether we want to favor SN2 or SN1. Whenever we have a nucleophile or base attacking an alkyl halide, we must consider elimination as a competing pathway. In SN2 conditions, a strong nucleophile can also act as a base and remove a proton, leading to an alkene. This is called E2. Bulky nucleophiles like tert butoxide strongly favor elimination. In SN1 conditions, the carbocation intermediate can lose a proton to form an alkene through E1. Heat and weak nucleophiles push the reaction toward elimination, so we have to think strategically. If we want substitution, we use strong nucleophiles in mild conditions. If we want elimination, we use bulky bases and heat. Let's see how these principles come together in real synthesis. For a primary alkyl halide like ethyl bromide, we use a strong nucleophile like cyanide in DMSO at room temperature to get clean SN2 substitution with inversion. For a tertiary alkyl halide like tert butyl bromide, water acts as a weak nucleophile in aqueous acetone, giving SN1 with a mixture of stereoisomers. If we want elimination instead, we use a bulky base like potassium tert butoxide in DMSO with heat to force E2. The key is matching your substrate structure, nucleophile strength, solvent polarity, and temperature to achieve your desired outcome. Now we're moving into aromatic halides, compounds where a halogen is bonded directly to a benzene ring. This CX bond is fundamentally different from alkyl halides. The aryl carbon is sp2 hybridized and part of the aromatic system, which makes the CX bond significantly stronger and much less reactive toward nucleophilic substitution. This difference in reactivity is crucial to understanding how aromatic halides behave in organic synthesis. We've covered the diazonium salt method, which is highly versatile. Now let's examine two additional preparation routes. The diazonium approach uses copper halides or potassium iodide to replace the diazo group with halogens, chlorine, bromine, or iodine, while releasing nitrogen gas. Alternatively, aromatic halides can be prepared directly from phenols using phosphorus pentachloride. When PCl5 reacts with phenol, the hydroxyl group is replaced by chlorine, producing chlorobenzene along with phosphorus oxychloride and hydrochloric acid as byproducts. Aromatic halides display interesting physical characteristics. They're typically colorless to pale liquids or solids with distinctive odors, and they're water-insoluble but dissolve readily in nonpolar organic solvents. Notice the boiling point trend. Fluorobenzene at 85 degrees C, chlorobenzene at 132 degrees C, bromobenzene at 155.5 degrees C, and iodobenzene at 188.5 degrees C. This increase correlates with molar mass and stronger van der Waals forces. Chemically, aromatic halides have two key components, the aromatic ring, which undergoes electrophilic substitution, and the halogen atoms, which are tightly bonded to the ring. This strong CX bond makes halogens resistant to nucleophilic displacement, quite different from alkyl halides, where the halogen is more loosely held and easily replaced. Physical properties are characteristics of matter that can be observed or measured without changing the identity of the substance itself. These include properties like color, shape, size, density, melting point, and boiling point. Unlike chemical properties, which describe how a substance reacts or transforms, physical properties describe what we can directly see or measure. For example, we can measure the mass of an object, determine its volume, or observe its color, all without altering what the substance fundamentally is. Understanding physical properties helps us identify materials, predict their behavior, and select them for specific applications. Aromatic compounds are organic molecules built around a benzene ring, a six-membered carbon ring with a special kind of stability. The benzene ring consists of 6 carbons arranged in a hexagon, each bonded to one hydrogen. What makes benzene remarkable is that its electrons are delocalized across the entire ring, creating resonance stability that makes it far more stable than we'd expect from a simple structure with alternating double bonds. This delocalization is why benzene and its derivatives, like toluene, phenol, and aniline, behave so distinctively in chemical reactions. The aromatic range acts as a stable core that can accept various substituents. Aromatic compounds undergo substitution through a two-step mechanism called electrophilic aromatic substitution. First, an electrophile, a species seeking electrons, attacks the pi electron cloud of the benzene ring. This forms a carbocation intermediate, where the positive charge is distributed around the ring. The key to this mechanism is that the ring's aromaticity is temporarily lost. In the second step, a hydrogen is removed from the ring, which restores the aromatic character and gives us our final substituted product. This mechanism explains why aromatic rings prefer substitution over addition reactions. They want to maintain their stable aromatic state. The position where a new substituent enters an aromatic ring depends on what's already attached. Electron-donating groups like hydroxyl or amino groups are activating. They make the ring more reactive and direct incoming electrophiles to the ortho and para positions, which are adjacent or opposite to the original substituent. Conversely, electron-withdrawing groups like nitro or cyano groups are deactivating. They make the ring less reactive and direct new electrophiles to the meta position. This happens because electron-donating groups stabilize the carbocation intermediate at ortho and para positions, while electron-withdrawing groups destabilize it everywhere except meta. Understanding these directing effects is crucial for predicting products in aromatic substitution reactions.